Hi everyone, welcome back to another GCSE Physics webinar. I hope you had a nice evening and you've had a chance to kind of catch up on webinars that you might have missed or be able to revise them. Today's webinar is going to be on atoms, radiation and the nucleus. As always, this session is 1 hour long and it will be recorded and uploaded onto YouTube later on in the day, so if you want to refresh and revise it, then you can. If you don't know me already, then my name's Preshayla and I'm the GCSE Physics tutor for the online school. I study physics at Loughborough University and it's my 4th year as a tutor. So what we're going to be covering today is what is radiation and how we can stop it. So we're moving on to a new topic of radiation, alpha, beta and gamma, that sort of thing. Understand what led to the discovery of the nucleus, understand different models of the atom and how they evolved, understand what scattering experiments are and how they helped us to understand the structure of the nucleus, know what happens to the atomic structure when radiation happens, and understand why some substances are radioactive and others aren't. We'll go through some example questions and we'll have time for your questions at the end. If you guys have any questions throughout the tutorial, then please don't hesitate to ask. Either put them in the chat or put them in the Q&A function and I will try to get to them as quickly as I can. Otherwise, we still have the Q&A session at the end. Okay, so let's quickly do a summary of the last webinar and indeed the end of the last topic. So we were talking all about gases and atoms and how they're kind of compressed. How does gas pressure affect volume? How does temperature affect pressure? So last webinar we looked at how does volume affect gas pressure, and we looked at this through the kind of idea of a piston in a container. So that container had a piston in it and we were pushing down on the piston to compress the gas, to make the volume of the gas smaller. When we made the volume of the gas smaller, we had to think about what happened to the pressure. Well, if we made the volume of the gas smaller, the pressure went up. And the reason for this is because the same amount of gas molecules are now in a lesser space. So they have less area to move around and therefore they collide against the walls more often. And hopefully you remember that those collisions create a force. And that force is what leads us to pressure. From pressure equals force over area. Okay, so it's this chain kind of process which starts off with the volume getting smaller, more collisions, more force, more pressure. So then we talked about this idea of work being done. Now remember, the definition of work being done is a force that is used to create motion. So the force that we were applying on the piston was creating motion, and that was our work done. The apparatus that we used to investigate Boyle's law was the cylinder of gas with the oil in, and it's attached to a pressure gauge. And so you can read the pressure gauge as you increase or decrease the volume of the gas. Then we talked about how this demonstrates Boyle's law, and at every single measurement you do, for each P, for each V, when you times them together, you're going to get the same number for every single reading. So if you want to have a refresher on that, then go ahead and go to the webinar on the YouTube channel, gas, pressure and volume. Okay, so let's talk about radiation. So in a couple of years ago, I mean not a couple hundred years ago, in 1896, there was this physicist called Becquerel, and he discovered the image of a key on a photographic film he developed. But he remembered that under that film in his drawer, there was a packet of uranium salts, okay? And so those uranium salts passed through the film, but not the key, okay? So there must have been some kind of particles, some sort of radiation, which was being emitted from these uranium salts, which hit the paper but not the key. And so Becquerel thought about this and asked Mary Curie, who was a young physicist in Poland at the time, to investigate. And she found that the salts were emitting radiation all the time. Okay, so radiation is this idea of a special type of particle being emitted from a material. Okay, and she used the word radioactivity to describe this property of uranium. So uranium was giving out some weird kind of particles that nobody could explain. And it was random, nobody could explain it. So she gave the word radioactivity to it, and they realized that uranium was giving out this weird sort of particle. But at the time, it was only uranium that they knew of. So they did more and more research on more and more elements, and they found lots and lots of different materials which were radioactive. So one of them was polonium, beryllium, and lots of different radioactive substances that they did experiments on and added to the list. Okay, so Rutherford then went on to put different materials between the radioactive substance and the detector. Okay, so he put different materials between the substance and the detector, and he found that one type of particle was stopped by paper. Okay, so if he put paper between the detector and the substance, one type of particle was stopped, but the other one went through the paper. And so he named these the first two letters of the Greek alphabet, alpha and beta. They were the first two particles that he discovered. And one went through the paper and one was stopped by the paper. So the one that was stopped by the paper, alpha, was pretty weak. It could be stopped by paper, and it wasn't very penetrating. Penetrating is this key word that we use to describe how kind of strong or weak the radiation is. So alpha is not very penetrating. It can really be stopped by paper, which is, if you think about it, a very thin material. Beta, however, goes through the paper. It cannot be stopped by paper, and therefore we say that it is more penetrating. Later on, gamma was found to be even more penetrating by both of them. So now Rutherford had found 3 different types of radiation: alpha, beta, and gamma, in order of penetration. So Rutherford carried out more and more investigations, and he found that alpha was composed of mostly positively charged particles. And the way that he did this is through his famous gold foil experiment. So what he did was he shot a beam of alpha particles at some gold foil. Okay, so he shot a beam of alpha particles at a thin sheet of gold foil, and he expected all of them to pass through, because it's just like paper, it's quite thin, and you know, he expected them to be able to pass through it. However, some of them rebounded. Okay, so some of them came back off of the paper, so they hit the foil and they came back. So he was confused as to why this would have happened. Why would the alpha particles be rebounding? Yes, they might not get through, but why should they come all the way back to the source? Well, he decided that this was because every atom at its center has a positively charged nucleus. Okay, so he proposed that the nucleus contained 2 types of particles, protons and neutrons, through this experiment. Okay, and we'll see more about this later. But in this diagram here, you can see that the alpha particles are hitting the atoms in the metal foil, okay, which are these pink dots. So our thin beam of alpha particles is hitting the atoms in the metal foil. And some do go straight through, but some bend and some get rebounded. Okay, and because of those that got rebounded, he was able to prove that the atom must have a positively charged nucleus. He knew that alpha was positively charged, and because the center of the atom was positively charged and they were repelling each other, he was able to prove this. So if you remember, a positive alpha charge and a positive center of the atom, if you bring two positive charges together, they will repel. Yeah, so if you bring two positive charges together, the alpha and the center of the atom, they will repel. And that's exactly what's happening when the alpha gets rebounded. It goes really, really, really close and then it shoots back because it's repelling that attractive charge in the center of the atom. So if we have two positive charges, they will repel each other. And that's exactly what he was able to prove. As well as this, he was able to prove that there is a positively charged nucleus and the nucleus is much smaller than the atom. Okay, so the nucleus is this pink dot here, and it's where most of the mass in the atom is, where all the protons and the neutrons are. But it is much smaller than the atom. It's only a small part of the atom. He was also able to tell that this was where most of the mass was located, in the center at the nucleus. So there were three deductions that Rutherford was able to come up with from this experiment. That it was a positively charged nucleus, the nucleus was much smaller than the atom, and the nucleus was where most of the mass was. Okay, so that is how he came up with the discovery of the nucleus. So then he went on to theorize the plum pudding model. So before the nucleus was discovered, before Rutherford did his experiment, other scientists didn't know what the structure of the atom was. And so they thought that there was a sphere of positive charge with little electrons dotted around it. Okay, so they just thought that each atom was simply a sphere of positive charge with electrons dotted around it, just like a plum pudding. So the electrons would be the plums, and the sphere of the positive charge would be the pudding. But Rutherford discovered that the plum pudding model was not true through his gold leaf experiment. Okay, so this became before Rutherford's gold experiment. So he disproved the plum pudding atom model. Okay, so we've had the plum pudding model, that's been discarded, that's wrong. And Rutherford's come along and said, okay, there's a nucleus, we know that it's positively charged, and we know that that's where most of the mass is, but we still don't know the proper structure of the atom. So we've discarded plum pudding and we've pretty much kind of taken Rutherford, but it's not the full story. So then Ball comes along, who's a new scientist, and he puts forward the theory that the electrons in the atom orbit the nucleus at specific distances and specific energy values. Okay, so every nucleus has electrons orbiting it. So now what they thought the atom looks like was this kind of central positive charge, some central positive charge with electrons orbiting around it. Okay, so this is what the new model of the atom was thought to look like. So instead of plum pudding, which was a sphere of positive charge with electrons dotted around it, we now had this idea that there was a central positive nucleus with electrons orbiting around it, just like the sun and the planets. Okay, so electrons are now these moving objects around a nucleus, and they were specific distances and specific energies of each of these little orbits. So we might have a distance x and we might have a distance 2x. So all that means is that they are specific distances from the nucleus. They're not just random orbits all over the place, very, very specific. And along with those specific distances come specific energies. So the first orbit has a specific energy, and this might be something like 2 times 10 to the 19 joules. Then the next orbit out might be double that, and so on and so forth. So we have these orbits which become known as shells, electron shells, that go out with distance and increasing energy. Okay, so each of these little orbits are called shells. Okay, so we know that we have shells and we know that we have a certain number of electrons, certain distances, certain energy values. But now Bohr comes along and he says electrons can move from one shell to another. So now what we have is our electrons jumping between shells. They could go to the shell below, or they could go to the shell above. So Bohr says these electrons can jump from one orbit to another. But how do they do that? Well, they can either absorb electromagnetic radiation to move away from the nucleus, so like this one here, or they emit electromagnetic radiation to move closer to the nucleus, like this one here. So they emit radiation to move closer, like this one here, or they absorb electromagnetic radiation to move away. And the reason for this is, if they absorb electromagnetic radiation, the electron gets the energy. It gets the energy from the radiation and it steals it. And therefore, it can jump to the next shell because it's been given some energy. Otherwise, it's going to stay there its whole life. But as soon as electromagnetic radiation comes along and bombards it, the electron steals it and can jump to the next shell. Now, with our other electron, which emits electromagnetic radiation, he loses some energy. Okay, so our electron loses some energy, and that means that it jumps down to the next shell. So it goes down a shell because it's losing energy and it has to go to the shell with the lower energy. It can't stay there anymore. It doesn't have enough energy to stay there. So it has to go to the next one down. Okay, so emitting EM just means electromagnetic. Okay, so emitting EM just means that it releases gamma, X-ray, microwave, radio wave, some sort of radiation to move closer to the nucleus. Okay, so that is how Bohr came up with his model of the atom. So we've gone from plum pudding, which is this idea of positive, a positive sphere with lots of little electrons dotted around it. Yeah, so he's come up with this idea now that says, okay, this plum pudding model was wrong. We need to come up with a new model to help us really understand the atom. And so he's come up with this new idea, which says that there is a nucleus at the center with electrons that orbit around it. Okay, so it's this positive sphere in the center, and now instead of the plums, we have the plums orbiting around. Okay, so they went on to do more and more experiments, more alpha scattering experiments, which showed that the hydrogen nucleus had the least amount of charge. So they did it on lots of different materials, lots of different elements, and they found that the hydrogen nucleus had the least amount of charge. And they also found that the charge of any nucleus is shared equally between a number of smaller particles, each with the same amount of positive charge. So now they've taken this central positive sphere, they've taken this sphere, and they've said, actually, it's not just a big blob of positive charge. It's lots of little positive charges. Okay, so it's not just a big blob of it, it's lots and lots of little positive charges. So this is another development of the model of the atom, which has now been able to be developed because we've done more experiments. So now we found that this central blob is actually lots of particles. And so they give the name proton to it. Okay, so they call these little positive charges protons. And actually they found that the proton was just actually a hydrogen nuclei. So you may note that on the periodic table of elements, hydrogen is just 1, 1. Okay, so if you've ever looked at a periodic table, you would see that it looks like this: hydrogen and 1, 1. We'll go on to talk about what that really means later. But what it means for now is that hydrogen is actually just 1 proton. The entire hydrogen nuclei is just 1 proton. But they found that actually the mass of hydrogen was bigger than just 1 proton, which was really confusing because at this point in time, they thought only protons existed and electrons. But they found that, okay, we know that hydrogen must only be 1 proton, but actually when we weigh hydrogen, it's much heavier. So there must be some missing particle that we don't know about. And they therefore called this the neutron. So you can see how the development has come all the way to finding the neutron. The neutron was actually the last thing to be discovered. Okay, so they just decided that there was some missing mass. There was some missing mass, and this must be coming from another particle. And they called this the neutron. Okay, so how does radiation change the number of protons or the number of neutrons. So how does emitting alpha or emitting beta radiation change the number of protons or electrons? Well, in beta decay, the number of protons change. So in beta, the number of protons change, and in alpha, the number of protons and neutrons change. Okay, so beta is just protons, alpha is protons and neutrons. Okay, I'm getting loads of comments that it keeps freezing, so I'm going to try to switch my Wi-Fi network. So just give me 5 minutes. Okay, hopefully that's better. Okay, we're going to go with that. Hopefully that's better for you guys. So yeah, changes in the nucleus from alpha and beta decay. Okay, so to be able to understand the number of protons and the number of protons and neutrons, Mendeleev, a new scientist, came up with this idea of showing it. So he came up with this AXZ model. So AXZ. And A was the number of protons plus the number of neutrons. Z was just the number of protons, and X was the chemical symbol. So X would be replaced with He, Ne, whatever the chemical symbol for that chemical was. The number of protons plus neutrons was A, and the number of protons was Z. So for example, for uranium, we have 92 protons, so 92 is the bottom number, and 146 neutrons. So 92 is the bottom number, and 92 plus 146 is the top number, because remember that's the addition of protons and neutrons. So he called he called Z the atomic number. Okay, so Z was the atomic number, which is the number of protons denoted by Z. Then he said that the mass number is A, which is the number of protons and neutrons. So here, this is the atomic, and here, this is the mass. Okay, so A is the mass number because it's the total mass in the nucleus, the protons plus the neutrons. That's what makes up the mass. The atomic number is the number of protons, which is Z. Okay, so two numbers that we need to know, A and Z. So let's have a look at this diagram here, this table here. This table says that the relative mass of a proton is 1, and the relative mass of a neutron is also 1. So we pretend that the mass of a proton is 1 and the mass of a neutron is 1. Okay, because they're roughly the same mass. However, the mass of an electron is so small. Okay, mass of an electron is only 1 over 2,000. Now, because it is so small, we just pretend that it's 0. Okay, so we presume that our mass for an electron is basically 0. So we say that all of the mass in the atom comes from the mass of the proton and the neutron. Not really the electron. The electron is so small that it has next to no effect on the mass. So we just say that it's basically 0. It's negligible. Yeah, the mass of an electron is negligible. It means it's so small, there's no point in counting it. So then we move on to the charge. The charge of a proton, as we know, is positive. Charge on an electron, as we know, is negative. But the charge on a neutron is 0 because it's neutral. So we have this charge and mass for proton, neutron, and electron. Now, there's another key term that we need to know, and it's this idea of an isotope. So isotopes are atoms of the same element with a different number of neutrons and the same number of protons. Okay, this can be confusing, so let's go through it in a bit more detail. Isotopes are the same element. Okay, so an isotope of one element is the same element, but a little bit different. So let's take uranium. So we've got 2 atoms of uranium. Same element, same material. And they have the same number of protons. Have the same number of protons, 92. So we'll write our 92 at the bottom here. Same number of protons. But they have a different number of neutrons. Okay, so for this one, let's say that we have 146 neutrons, which makes our total 238. But our isotope has a different number of neutrons. So our isotope might have 144 neutrons. And because it has a different number of neutrons, our mass number will be different. Our mass number will be 236. So you can see that we have the same element, the same number of protons, but a different number of neutrons. And because we have a different number of neutrons, our mass numbers are different. So we say that this element on the right is an isotope of uranium. This is the normal uranium, but this is an isotope of it. Okay, so remember the definition for an isotope is the same number of protons, different number of neutrons. Okay, so let's look a bit more into each type of radiation. So let's start with our first radiation, alpha. Now, alpha can either be depicted as this little fish sign or helium. Okay, so this is an idea that we've not looked at before. Alpha is actually a helium particle. It's a helium nucleus. Alpha emission, alpha radiation, all it is helium. Really weird to think about. Okay, so if alpha is a helium nucleus, That means alpha has 2 protons, as we can see here. It has 2 protons, 2 protons and 2 neutrons. Because remember, 4 is 2 protons plus 2 neutrons. So it has 2 protons and 2 neutrons. Its mass, therefore, is 4, and its charge is 2. Its charge is 2 because it has 2 protons. It's identical to a helium nucleus. Okay, absolutely identical to a helium nucleus. Now, when alpha gets emitted from a source, some radioactive substance, the atomic number goes down by 2 and the mass number goes down by 4. So the atomic number, the number of protons goes down by 2 because it loses 2 protons. And the mass number goes down by 4 because it loses 2 protons and 2 neutrons. So we show this in a sort of equation, okay? Not the equations that we're kind of used to seeing, but more of a flow equation. So let's give you an example. We start with an element. Let's take thorium. So we're just starting with a random radioactive source, substance. So we're starting with thorium. Now, thorium undergoes alpha emission. So you might be told in the question that thorium undergoes alpha emission, alpha radiation. So the next thing to do is to draw our arrow and put alpha in. You can put alpha or you can put helium. It's completely up to you. For this one, we're just going to put alpha. Now we know that alpha has a mass number of 4 and a proton number of 2. So you can see that we're lining up the proton numbers and we're lining up the mass numbers. So I want you guys to have a think. What might go here and here for our new element, radium? So the left-hand side needs to equal the right-hand side. So what might be the new mass number and what might be the new proton number? Put your answers in the chat. Let's see if you guys can have a go. What's the new mass number and what's the new atomic number? Put your answers in the chat. What do you think the mass number might be? And what would the proton number be? So remember, 90 needs to equal this plus this, and 238 needs to equal this plus this, the two mass numbers added together. So what do we think it might be? Okay, so the new mass number is 234 because our element loses, mass number goes down by 4. It loses 2 protons and 2 neutrons. Our proton number is 88 because it loses 2 protons. Okay, it goes from 90 to 88. It loses 2 protons in the form of alpha, of helium. So because thorium loses this alpha particle, this helium particle, it gets turned into a new element. So now thorium changes into radium plus alpha. Now, why does it have to be radium? And the only reason it has to be radium is because I've gone to the periodic table and looked at which one has 234 and 88. Okay, so you will most likely be given what element it turns into. I don't think you're given a periodic table to have to do that bit yourself, but what you might have to do is work out what has been emitted. So is it alpha, is it beta, is it gamma? And then you'd have to fill in this bit here. So the reason that I knew it was radium is because I went to the periodic table and checked which one was 234 and 88. Okay, but lots of different reactions will have different products. So beryllium might go to radium, and so on and so forth. You don't know. Yeah, you have to just check the periodic table. But you won't have to do that in an exam. As I said, you will need a periodic table to do that. So the only way that you're going to be able to work it out is by already having the element there, or by filling out what's here. Okay, so we know that alpha is just a helium nucleus. Okay, so what is beta? Well, beta is just an electron. So given these really fancy names, but actually all it is a helium, electron, and a wave. So it actually boils down to something really simple. So beta, all it is an electron. And the neutron is able to change into a proton plus an electron. This is what happens when beta happens. The neutron goes a bit like weird, and it turns into a proton and an electron. Happens really random. Nobody knows kind of why it happens. It's really random. But what happens is this neutron changes into a proton plus an electron. So it emits an electron in the form of beta, which is depicted by this weird looking B here. So it's B, but you extend the tail a bit. Okay, so when beta is emitted, the neutron gets turned into a proton. Okay, so the mass of a beta particle is 0. It doesn't have any protons, it doesn't have any neutrons. But what it does do is make the proton number decrease by 1. Okay, so it loses a proton. So the atomic number will go up by 1 here, and the mass number will be unchanged. So what an equation might look like is this. We start with some radioactive substance. In this instance, we'll have potassium. Now our potassium is going to change into a new substance by emitting a beta particle. The beta particle is 0 at the top and -1 here. So what would we fill in for our mass number and our proton number? Put your answers in the chat. What would the mass number be and what would the proton number be? So we're changing potassium by emitting a beta particle. So what would our atomic number be and what would our mass number be? So 90 needs to be this -1, whatever this is, -1, and 40 needs to be whatever this is, +0. So we know that 40 stays the same because the mass number is unchanged. And the proton number goes up by 1, 20. The atomic number is 20. 20 -1 is 19. So this sum here, 20 - 1, needs to equal this here. So these are our radiation equations. Finally then, let's look at gamma. So all gamma is electromagnetic radiation. It's the easiest one, it's a gamma ray. If you remember back to when we did the electromagnetic spectrum, all gamma is that far end of the spectrum, gamma rays, gamma waves, it's just electromagnetic radiation. It's uncharged and it has no mass. So it might look like in a diagram, this is gamma, 0. Okay, so this gamma, like upside down fish, 0 and 0, no charge, no mass, nothing. It doesn't change the number of protons and neutrons, it's simply a wave of gamma electromagnetic radiation. So to recap, we have alpha is our helium nucleus with 2 protons and 2 neutrons. Beta is just an electron. And gamma is just a wave, an electromagnetic radiation wave. Uncharged, no mass, doesn't do anything to the protons or the neutrons. Now we have another one, which is not one of the formal ones. You still have alpha, beta, and gamma. We have another one, which is less common. And this is called neutron emission. Now, neutrons are emitted if an alpha particle collides with a nucleus. So nucleus is made up of protons and neutrons. So this is our nucleus, and an alpha particle comes in and bombards our nucleus. And if that happens, then a neutron goes flying off. So alpha hits the nucleus, the neutron goes flying off. Now these collisions make the nucleus even more unstable. Okay, so neutrons make the nucleus unstable. Alpha, beta, and gamma make the nucleus more stable. So if it's going to emit a neutron, it's going to become more unstable. But neutrons are uncharged and can pass through easier than alpha or beta. So why are some substances radioactive and others aren't? Well, we already know that every atom has a nucleus with protons and neutrons. The electrons move around in little shells that surround the nucleus. Most atoms have a stable nucleus, but some don't. An unstable nucleus becomes stable or less unstable by emitting alpha, beta, or gamma. So the reason that some substances are radioactive and others aren't is to do with how stable their nucleus is. If they have an unstable nucleus, they will emit alpha, beta, or gamma randomly to become more stable. Okay? So the important thing about alpha, beta, and gamma radiation is that nobody knows when it will happen. We cannot predict it. We can predict a lot of things in physics, but we cannot predict the emission of alpha, beta, or gamma. Now, how do we test the radiation that is being emitted? Well, we use this apparatus called a Geiger-Müller counter. Now, the Geiger-Müller tube is connected to an electric counter. So this is our electric counter. This is the tube here, the Geiger-Müller tube. And the counter clicks every time a particle of radiation from the radioactive substance enters the Geiger tube. So we might have our radioactive substance here. You put the Geiger-Müller tube near it, and it picks up all this radiation that is flying off. So it picks up all these little alpha particles, beta particles. into the tube. And every time it picks one of those up, it clicks. Okay, so that's all the content for today. I know there's been quite a lot of content and we have gone through it quite quickly. So I'm going to answer some questions now. And I know that the sound was also being quite dodgy. So if there's anything that you missed completely, then just let me know on the chat and we can go over it. Okay, so someone said, do we need to know this experiment right at the beginning? And I'm assuming you mean this one. Yes, you do need to know this experiment. You need to know the gold foil experiment and how, because some of the particles were rebounded, this told us that there must be a positive charge, because we knew that the particle of alpha was positive and it was repelling. So there must be another positive charge somewhere because there's repulsion happening. Is there a limit on how many electrons can be in a shell? This is a really good question and one that you will cover in chemistry. But for now, let me just tell you that yes, there is a limit on how many electrons can be in a shell. So in the first shell, you can only have 2. In the next shell, you can only have 8. In the next shell, you can only have 8, and so on. And the electron will fill up a shell before it moves on to the next shell. So if there's, let's say, 3 electrons, it puts 2 on the first shell and then it puts 1 on the second shell. So yes, there is a limit. If many electrons lose EM radiation, then can the atom's shells hold it? Okay, this is interesting because the electron will not lose electromagnetic radiation if there's nowhere for it to go. Okay, so if this electron was trying to go onto this one, it would now be a 3, 8, 8, 1, and it would become ionized. Is the atomic number always on the bottom? Yes, it is. The atomic number is always on the bottom. This is the standard procedure for writing out elements. Atomic is on the bottom, mass is on the top. Is carbon dioxide an isotope of carbon? Okay, interesting question. Not quite. Carbon dioxide is a mixture of carbon and 2 oxygens. So carbon dioxide, the chemical symbol for that is carbon over 2, because there's 2 oxygens, dioxide, and carbon. So carbon dioxide is a mixture of 2 elements within itself. It's not an isotope of carbon, but there are isotopes of carbon. What does the word alpha mean? So alpha is simply a Greek letter. It's the first Greek letter in the Greek alphabet, and it looks like this. That's all alpha means. How many electrons does alpha have? None. Alpha doesn't have any electrons. Alpha is only the nucleus of helium, not the electrons in helium, just the nucleus of helium. Okay, so it's only the protons and neutrons. Will we get less marks if we put helium? Absolutely not. You can have He or you can have alpha. It's completely up to you. Do you need a full outer shell for an atom to become stable? Yes. What if all the electrons emit protons, so they all go close to the nucleus and break the allowed number of protons on each shell? Okay, so this is when it becomes ionized and it becomes charged. Who discovered the nucleus using gold film experiment? Rutherford. Okay, I think that's all the questions. Let's quickly go through an exam question. So this is a typical exam question which comes up a lot, and it's a 6 marker. And it says that some substances are radioactive. They may emit alpha or beta particles. Describe the characteristics of alpha particles and beta particles in terms of their structure, penetration through air and other materials, and deflection in an electric field. Don't worry too much about the third one, as we're going to cover that tomorrow. But you need to talk about the structure of the alpha particle. And what you would say here is that the alpha particle is a helium nucleus with 2 protons and 2 neutrons. The structure of beta is simply an electron. And that's what you would be saying to get your first 2 marks. The second 2 marks come from talking about the penetration through air. So as we said right at the beginning, alpha is very weakly penetrating and can be stopped by a single sheet of paper. Okay, so it can get through air really easily, but it can be stopped by a single sheet of paper. Beta is more penetrating than alpha. And that's all you'd have to say for that bit. Okay, and then the deflection and electric field will come back to tomorrow. So as long as you make sure you tick off each bullet point in a 6 marker, you'll be fine. And it's usually 2 things that you're comparing, or 3 things, and you just have to say each feature about each kind of particle. Here's another question. So the particles in the nucleus of an atom are protons and neutrons. So a nice easy one to start off with. In the nucleus, we only have protons and neutrons. In the atom, we then have electrons orbiting it. Yeah, so the whole atom has protons, neutrons, and electrons, but the nucleus, which is the inside central bit where all the mass is protons and neutrons. Complete the table to show the relative charge of the atomic particles. Electron is -1, proton is a positive charge +1, and neutron is 0. It's a neutral 0 charge. A neutral atom has no overall charge. Explain this in terms of its particles. Well, what that means is the number of protons equals the number of electrons. And the reason that this works is because the total positive charge of the protons equals the total negative charge of the electrons. They therefore cancel out and we get a neutral atom which has no overall charge. So we're going to stop with the questions there. We have less content to cover tomorrow, and we have a whole section dedicated to exam practice. So we'll be doing loads of questions and less content tomorrow. So yeah, thank you for attending this webinar. Hopefully you're attending some other webinars today. And I will see you for another physics session tomorrow. As always, it will be uploaded onto YouTube. And if you want more kind of one-to-one personalized style tutoring, then that's something that MyTutor offer, and you can sign up to one-to-one tutoring with a tutor like me through MyTutor. So yeah, that's everything, and I will see you guys tomorrow. Have a nice evening.